Hello, welcome to this video. So it's now kind of Advent, we're in December. Given it's December, lovely night sky, brilliant time to talk about space. And so I thought I'll make the two-part video on the potential of using ideas in special relativity to help with space travel. Now, when I originally began doing these videos, I forgot to include length contraction in my calculations. And consequently, I ended up predicting something which is rather absurd, and which wouldn't be the case. But predicting that shows the importance of length contraction, and length contraction could be used in principle in the future to help us travel to distant stars, maybe even distant galaxies within our own lifetime, despite them being, from our current perspective, a huge distance away, far further than light would travel during the average human lifespan. Given that I didn't include length contraction, something went rather wrong with my calculations initially, and I considered, not posting this video and just maybe going to a video with length contraction included. However, I feel that wouldn't really show the process of science, and I feel as part of this channel I want to be as open with you as possible, and part of being open is kind of showing the scientific process as it genuinely happens, because although it's not often talked about, particularly from a historical perspective, science is full of trial and error. And you can actually learn a lot from if something goes slightly wrong in calculations. And it's important to play with maths and to be able to analyse maths even when it goes mildly wrong. So I'm making this video to talk about why we need length contraction, which I realised as I was making this video I reached some rather absurd conclusions. And it turns out that without length contraction, we run into a problem where if an object starts to, get very close to the speed of light, its velocity, it would appear to us like it would be slowing down, even though from its perspective it would be speeding up, and this causes quite a significant discrepancy in the velocity of the object, which would run, into mass conflict, where we would have physics start contradicting itself from one frame to another. They wouldn't just be relatively different, they would start to conflict in ways that would be troubling. For example, if a spaceship moves at a velocity v away from you, that spaceship should think that you are moving away from it at a velocity of minus v, or at least the size of the relative velocity should be the same. And that's because velocity is relative, so whether you or the ship is stationary is just a matter of perspective. Most certainly the size of the velocity shouldn't be different. That is, you shouldn't think that the ship is moving away from you at a different speed to the speed somebody on the ship would consider you moving away from them. So, to prevent that happening, we need length contraction, but now I'm going to show you what happens if we don't include length contraction, so that we get to this rather bizarre effect. So let's have a go at finding the velocity of a spaceship, where our setup is we've got a spaceship which is moving. Well, the spaceship thinks it's moving at a velocity v away from the Earth, but if you're on the Earth, you think the spaceship is moving at a velocity v prime away from you. Now, with length contraction, v and v prime would be the same, but without it, thanks to the phenomenon of time dilation, these are not going to be the same, and hence we run into problems. But that's kind of go about deriving this and showing this. So remember, v prime is the speed of the ship or spaceship as it's moving away from you, according to your own perspective if you're on Earth. Whereas v is the velocity the people on the spaceship think they're moving away from you. Now, if we're not worrying about length contraction, the distance the spaceship is moving is the same from the reference frame of the people on the spaceship and from the reference frame of the Earth. So we can just call this distance ds. But due to time dilation, dt prime and dt are going to be different. Now, a question comes about of how we're measuring the passage of time. Well, I'm thinking of we're measuring time as there's like a light source on the spaceship, which could be the spaceship itself because it's emitting visible light, and say every millisecond or so, a stream of photons goes from the spaceship to the Earth, and that's every millisecond from the perspective of people on the spaceship. But due to time dilation, that time interval from the perspective of people on Earth actually gets longer and longer as the speed of the spaceship increases. So if the time interval is dt on the spaceship, it's dt prime from the perspective of people on Earth. And therefore the velocity of the spaceship from the perspective of people on Earth, so v prime is just ds by dt prime, where dt prime is given by multiplying dt, so the time interval on the spaceship, by gamma, where gamma is your Lorentz vector. And we talked a lot about time dilation on this channel, and particularly on this playlist, so I won't go over the time dilation really in much more detail, but the overall effect is that we have the velocity the ship is moving according to people on Earth, so v prime, equaling the velocity the spaceship thinks it's moving at, divided by your Lorentz vector gamma. So clearly v prime and v here are different. And this would actually break one of the core principles of relativity, with that core principle being, all reference frames are equivalent, and therefore people on the spaceship should see the Earth moving away from them at the same speed that people on the Earth see the spaceship moving away from them. So clearly a discrepancy between v and v prime is troubling. And if we write this, explicitly in terms of v and c, so we replace the Lorentz vector with its explicit representation in terms of the velocity of the spaceship according to the spaceship, we end up with this equation. Now here gamma is a function of v, not v prime, because time dilation is, it's debatable really. I put gamma as a function of v because I'm supposing the time dilation is coming from the movement of the spaceship, which is moving away at a velocity of v. You could also plausibly say, well, it should be v prime. If you include length of contraction in the argument, v and v prime are the same. If you don't include length contraction, then v and v prime are not the same, so it's debatable which gamma factor to use. But what we're doing already breaks relativity, so this is just showing that we do run into problems. But anyway, if we stick with gamma being a function of v, then this is the curve we get with v prime on the y-axis and v on the x-axis. And what you can clearly see is that for low velocities, where v and v prime are small, v and v prime are very similar. The graph, our red curve, traces out a path which is very similar to the path traced out by the line y equals x, or in our case v prime equals v. However, as the velocities get larger, this curve deviates from v prime equals v, and at some point, if v increases, that corresponds to a decrease in v prime. So if the spaceship moves fast enough, as it keeps moving faster beyond that point, according to people on Earth, the speed of the spaceship will slow down, which I think is quite troubling. And as a summary, here are the kind of important things to note. So before critical point, an increase in v corresponds to an increase in v prime, and then after the critical point we get this bizarre behaviour where the spaceship seems to move faster from its own perspective, but Earth sees the spaceship moving slower. The graph I have here I quickly got from a online graphical calculator, a free one. I would always recommend using a free online graphical calculator rather than buying a graphical calculator, because there's perfectly very good free online websites. But I made a kind of like more detailed graph on the next slide, and well, additionally, as well as the graph, I've worked out this critical point where an increase in v corresponds, well, to a decrease on v prime, and we'll look at that in a bit. So now we've had a little look at how v prime and v relate as a function. We've had a little look at the shape of the curve, although we'll talk more about the graph on the next slide. Let's find the point at which this shift occurs between how v and v prime relate. So the point at which an increase in v stops causing an increase in v prime. Now we call this critical point in the language of calculus. We call this point a stationary point. We do that because one of the first really uses of calculus from a physics perspective was in mechanics. And one of the most straightforward graphs you can plot in mechanics is plotting distance against time, or displacement against time. And if you have a stationary point on that curve, that corresponds to the object at that moment in time, essentially not moving. So at that moment, maintaining a constant distance or displacement. Hence why we call these things stationary points. But we can find a stationary point for the prime v relationship. And we do that using kind of the rules of differentiation. So it's also a good way to practice going over how to differentiate functions. So our function is v prime as a function of v, which we can write in this form. Now, in the bottom equation, I've just rewritten the top equation, to have it in a slightly neater form. I've done that because it's easier to differentiate v prime as a function of v if we have just, v's by themselves, whereas having v squared over c squared within a square root just will introduce lots of factors of c which are unnecessary. So I just take the c out of the fraction within the square root. That just makes the task of differentiating a little easier and makes it less likely we get run to accidental errors along the way. Although I'm only human, so forgive me if there are any errors. Although I've gone through it a few times, so I think we're all good. So if we do dv prime by dv, so we're differentiating our curve. We can firstly use the product rule, because v prime as a function of v is kind of the product of, if you like, two functions. One of the functions is just linear in v. The other function is a bit more complicated. It's the one the square root. So it'd be the square root of c squared minus v squared. So if we do the product rule, we differentiate v over c, which just gives us 1 over c, and then we multiply by our other function, so the square root of c squared minus v squared. But then, to product rule, we have to add v over c times the derivative of the function, the square root of c squared minus v squared. And you can do that using the chain rule, and you'll end up, overall getting to the top equation we have here. Then we can just kind of neaten up the second term a little, so collect factors of v, cancel out our, fraction of a half by our times by 2, and we end up with this middle expression, and then our bottom expression, once we've newtoned things up a little bit more by factorising out the 1 over c, we get this. Now this is quite long and a bit bulky, so let's bring in our good old friend the Lorentz factor back, and when we do this we end up with this expression for how, for the gradient of our function v prime as a function of v. Now you can see that there's a minus sign, and that minus sign allows the gradient for certain values of v to go from being positive to being negative. And we can also see, for small values of v, v over c squared is going to be negligible, so we have a positive gradient because gamma, our Lorentz factor, will be positive. Whereas for large values of v, so as v's get close to c, although gamma is huge, 1 over gamma will correspondingly be tiny, so we can ignore that term, leaving us with just gamma v squared over c squared, which is going to be quite significantly big because gamma is quite big, so we have a large negative gradient. And it's often, once you have an equation, good to look at it and just kind of work through it in your head to check it makes sense and matches figures you've seen before, such as graphs. So now we're going to use our value for the gradient, or a function for the gradient, to find the stationary point. So the stationary point is when dv prime by dv is 0, which, if you use the expression we had for the gradient a moment ago, you'll end up with saying that the critical point will happen when v is about 0.7 times the speed of light. So when the spaceship, from its perspective, is moving at 70% of the speed of light, and then if you calculate the speed that the spaceship is moving from the perspective of Earth, you can do that by putting just v into your function to give you v prime, and you'll end up with v prime is c over 2, so half the speed of light, or 50% of the speed of light. So the critical point will happen when the spaceship is moving at 50% of the speed of light, according to people on the Earth. And we can see this clearly if we look at the graph I plotted. So on the y-axis we have v prime, so the velocity of the spaceship from the perspective of people on Earth, and we can see it peaks neatly at about 50% or 0.5 times the speed of light, whereas v is along our x-axis, which is the speed of the spaceship from the perspective of people in the spaceship, and the peak occurs when v is about 0.7 times the speed of light, so 0.7 on our x-axis. So this has been a rather interesting video for me to do, because it's a video of kind of like showing really why we need a length contraction to prevent this kind of bizarre effect from happening, to prevent v and v prime not only being different but changing how they correlate to each other at a critical point. But it's also good to do this video because science is full of kind of like people having a go at a problem, taking a few wrong turns, and then at the end of it coming out with something really promising. And you can only find the right avenue by exploring other avenues. And also, though, it's a good way to practice playing with different models. And it's like, just as you don't realise sometimes the value of things till you miss it. Similarly, you don't realise the sometimes importance of certain principles until you're working, in the late evening, and then find that you happen to miss out an idea in all your excitement. So, quite a good video, I think, for showing the progress of science, as well as a interesting thing of what would happen if it weren't for length contraction also occurring. And this video therefore also emphasises that we need to consider space-time in a unified manner, because if you just deal with time dilation, you don't include length contraction, you run into quite serious problems. Time dilation necessitates length contraction if we want to preserve the idea that v prime and v should, at least maintain a consistent correlation, and definitely if we want v and v prime to be the same. So that's everything for this video. In the oncoming video in the playlist, although I'm planning to release them together, so it should hopefully be there by the time you're seeing this, we'll go through what length contraction would have to be if v prime and v are going to be the same.